Guys, Guna Math here, and this is the 2021 Stanford Math tournament, and this is the number theory section. This is problem number 1 over here. It states that for some positive integer n, 2021 minus 2 times phi to the n can be expressed as the sum and difference of distinct integer powers of phi, and we want to find phi to the n. Now, first thoughts is when we see this integer powers of phi, we want to think base phi representation, because in the base phi representation we get powers of phi. So how can we convert this into a base phi representation where we can easily see the powers of phi? So firstly, what we can do is we can convert 2021, which is in base 10, to base phi. To do that, we can easily just list multiple powers of phi. We know that we don't have to go past 625, which is phi to the 4th. There's 125, 25, phi, and 1. To get to 2021, we need 3 625s. That gives us 1875. We have 146 left over. We can take 125, so we have 21 left over. We can take 4 5s and 1 1. And this is a 0, because we don't need a 25. So this is basically equivalent to 31041 in the base phi world. Okay, so now we have 2021 in base phi. Let's see how we can get the 2 times phi to the n in base phi. Well, phi to the n, that's rather simple. Let's make a chart. For phi to the 1, where n is just 1, well, the phi to the 0th place will be empty, and for phi to the 1 place, we'll need 1. For phi squared, the 0 and 1th place will, the 0 and these two places will be empty, and then we need a 1 over here. For phi cubed, it's 3 zeros. Phi to 0, phi to the 1, phi squared, and the phi cubed, and so on. So in general, of course, if this pattern wasn't immediately obvious, we see that phi to the n has a 1 followed by n zeros. So, and 2 times phi to the n would simply be just changing this 1 to a 2. So we know that this is basically 2, and then how many ever n zeros after that. So now let's look at 2021 minus 2 to the phi to n, 2 times phi to the n in base phi. So we have 31041 minus this whatever, and then in base phi. So now we want to kind of carefully construct how we're doing our subtraction. It needs to be expressed as a sum and difference of distinct powers of phi, meaning that we can't have a coefficient other than 1 for the phi's. Base phi representation is good, but for some of these we have a coefficient that's not 1, which doesn't result in a power of phi. For example, this one would be 3 times phi to the power of 4, which is not a power of phi. We want to make sure that leading coefficient is 1 or negative 1 possibly. So let's think of how we can achieve that. Well, if we have basically a power of phi, like leading coefficient of 1 and a power of phi, then we're done. This is just already expressible as a sum and difference of distinct powers of phi. And then we can also do the same thing for 4. If we have 4 times phi to the j, for example, we can just do some quick algebra, write this as phi minus 1 times phi to the j, which is nothing but phi to the j plus 1 minus phi to the j, which is the sum and difference of powers of phi. So we want to construct this subtraction such that we get 1s and 4s, and zeros also, because the zeros will just disappear once we represent this in base 10. So 1s and 4s we're looking for. We know that 2 to the phi of n is just 2 with n zeros followed, so we can place a 0 here, we get a 1, that's good upon subtraction. We can place a 0 here, we're good. We can place a 0 here, we're good. We can place a 0 here, we're good. And then over here, I think we can cut it off, and we can say this is 2. So we have the subtraction taking place. This is just 1, 4, 0, 1, 1, base phi. Now we can go ahead and evaluate this, and then and then put this in base 10 and then solve for n. But then by our construction, we know that n is 4, right? N is 4, because there are 4 zeros at the end. So our answer is just compute phi to the n, which is phi to the 4th, which is 625, and we're done.